Hello, everyone. For those of you who don't know me, I'm Robin Morris, convener of the Oxford Energy Network. Thanks very much for coming and for people joining online. This week, for our Oxford Energy Network Seminar, we're delighted to have an international visitor, and it's Professor Lucy Powell from the University of Colorado, Boulder. So, very brief background. Prior to arriving at Boulder, you earned your bachelor's and your master's at Stanford in electrical engineering, and you completed a number of sabbaticals at Harvard, Berkeley, NREL, and institutes in Germany. And I guess you're currently on a local sabbatical. In other words, it's in Europe, so it's quite low. Perhaps best known for activities in large-scale wind development, Lucy's research covers a wide gamut of topics, from control systems through multi-sensor fusion to haptic and multimodal interfaces. But if you excuse my mixed use of units, she encompasses scales ranging from megawatts at one end, wind turbine systems, down to nanometers, not quite same units, atomic force microscopy and disk drives, but that's control. Control can cover a huge range, decades, even different units. But with last week's news that Andrew Garrard was joint winner of the 2024 QE Prize around development of the early stages of wind energy, it's a timely opportunity to look at wind power, and we look forward to hearing from Lucy more about that. Just to briefly say, Lucy is around for the rest of this week, and Jack Ummenberger at the back is helping to coordinate the visit if anyone else would like to get to meet with Lucy. And there's also a control system seminar tomorrow afternoon at 2 p.m. in IEB, Information Engineering Building. But Lucy, I hope we're going to be hearing from you about challenges in design and operation, but also how some of the improvements have been realised, and really just recognising that wind's got a very important contribution to clean energy technology. So, floor is yours.
Great. Thank you so much for the nice introduction. It's great to be here. It's good to see everyone. So, as Robin mentioned, I'm currently on sabbatical. I'm actually locally coming from the Eindhoven University of Technology, where I'm there until the summer. And when I'm not on sabbatical, I'm at the University of Colorado, Boulder. And these are some aerial photos of our campus. That's the engineering center on the right. And I was going to ask how many people here have actually been to Boulder? Actually, quite a few.
You're jealous of your mentioned hills.
So this is a larger aerial photo. Yeah, so in Boulder, we're at the foothills of what are called the Rocky Mountains in the United States. And for those of you who are less familiar, I'll show you where Colorado and Boulder is. This is a wind map of the U.S. And in the U.S., we have really good wind resource in the center of our country. A lot of wind farms have been built there. So Colorado is this rectangular state. We're on the western edge of that so-called wind belt. We do have a number of wind farms on the eastern edge of our state. So Boulder is approximately there. And the Rocky Mountains run roughly north-south just to the west of Boulder. So the closest major city is Denver. It's about 25 miles southeast of Boulder. And then another location of interest is the U.S. National Renewable Energy Laboratories National Wind Technology Center is located just about 7 miles south of our campus. And they've been a great resource. We've collaborated on many projects with NREL researchers, and we've been able to test out some of our advanced control algorithms on research turbines at the NREL site. And I'll briefly talk a little bit about some of the field testing we've done there recently. Right. So what I thought I would do is first talk about sort of where we are now in terms of installed wind power capacity worldwide, and then talk about a couple of projects, hopefully areas that can help wind energy develop further in the coming years. My group has been involved in investigating 2-bladed and 3-bladed lightweight downwind boilers. I'll talk a little bit about that project. And I'll also talk about floating wind turbines, the project that we've worked on there. First, where are we now? So we're going to look at this decade from 2013 through 2022. And over this decade, worldwide, The average annual growth rate for installed wind power capacity is 12% per year. So at the end of 2022, there was 906 gigawatts of installed wind power worldwide. Now, by country, which country has the most installed wind power? China, definitely, by far. So China has about 40% of the world's installed wind power capacity. Now, what country is number two? It's not UK. It's not Germany. It's actually US. And then what country is number three? Not quite UK. So it's actually Germany. So UK is number 6 in terms of installed wind power capacity, but in terms of generation, UK is actually 4th. So I did plot the UK on here, and on this scale, it doesn't do it justice. I plot it on its own scale. So the UK has, at the end of 2022, almost 30 gigawatts, about half onshore, half offshore. And the UK is aiming to expand offshore wind from the current 15 gigawatts to 50 gigawatts by 2030. So if we look at the wind resource around the North Sea, dark red's a really good wind resource. UK has really good wind resource, both onshore and offshore. Okay, so this pie chart shows the top 10 countries in terms of installed wind power capacity. And there's quite a bit of installed wind power capacity in many other countries worldwide. Now, you're a small country, comparing by wind power capacity, maybe not so fair. And so comparing by wind penetration might be a better measure. So wind penetration is what percent of a country's electrical energy needs is being met by wind. And in this regard, Denmark is by far the #1 country. More than half of Denmark's electrical energy needs is met by wind. And these are averages across the year in 2022. And so instantaneously, Denmark does at times reach 100% wind penetration, at which times they're trying to export a lot of that wind power to neighboring countries that can better use that power at those times. So China, for all its installed wind power capacity, very large population, large electrical energy demand. It's only at 9% wind energy penetration. The US, we have lower population, but unfortunately we're energy hogs, so we're only at 10% wind energy penetration. So the UK in 2022 is about 25% wind penetration. I understand it's about maybe 32% now. Okay, but the point of this is that there's still a lot of room to grow. Solar penetration in general is behind wind penetration. It's catching up quickly and will surpass wind soon, but there's still a long ways to go for trying to get to 100% clean energy penetration. So what are some of the things that we've been studying in my group to hopefully push wind energy further? One area is looking at lightweight downwind rotors. Another area we've been looking at is in floating wind. So let's first talk about the downwind lightweight rotor concept. But before getting into that, let me just briefly go over the main components of a wind turbine so we're all on the same page. So this is a photograph of a 1.5 megawatt wind turbine that's at the NREL site just south of my campus. It's a traditional 3-bladed upwind turbine. So the wind is coming in from the left. There are 3 blades. They come together at what's known as the hub. The hub together with the 3 blades is called the rotor. That's the rotational part of the turbine. The rotor is mounted to the nacelle. The nacelle also houses the drivetrain and generator, and the nacelle is on top of the tower, and the tower is secured into foundation, which for land-based turbines is a lot of concrete, because meters deep, and these days is tens of meters across. So I brought in a plastic little model of the turbine just for fun, which we can pass around. And so The standard wind turbine is a three-bladed upwind turbine, faces into the wind, so the wind comes through the rotor first before going around the tower. If we turn the other way, then it's a downwind rotor. So then the wind will go around the tower first before going through the rotor. Oh, there's a down. All right. So many people are familiar with wind turbines just getting larger and larger. Over the last 30 or so years, wind turbines have gone from about 100 feet at hub height with 90-foot rotor diameters now to well above 300 feet at hub height and about beyond 500 feet rotor diameters. Now, for land-based turbines, we don't see more than about 5 or 6 megawatt turbines. And this is largely due to transportation constraints on land. So roads and railways really don't allow towers and blades for larger turbines to be transported. So the really large turbines are all for offshore wind. So for offshore wind, there are 13 megawatt and 14 megawatt turbines that are being built in large wind farms that are going to become operational this year. There are 15 megawatt commercial wind turbines that you can order now. They will be ordered for newer wind farms that are being planned. And so we will get to the 17 megawatt turbine, I think, well before 2035 commercially. So when we see wind turbines, especially these large offshore turbines, typically we're looking at them from a distance. It's sometimes hard to appreciate just how large they are. They're the silhouette of the Statue of Liberty, but in case you're not as familiar with that, I've also included an Airbus A380, kind of the jumbo jet for intercontinental travel, and also a regulation size soccer football field. So if we superimpose these onto the 6 megawatt rotor plane, you can hopefully appreciate just how large these wind turbines are. And remember, we have 13, 14 megawatt turbines that are being built in large wind farms as we speak. Okay, so part of the economy of scale in going to larger wind turbines is that power is proportional to the cube of wind speed, and there's typically higher speeds as you get higher off the ground. And so having taller towers allows us to access those higher speeds. Power is also proportional to the rotor swept area. And so taller towers can also hold up much larger rotor. So of course, the rotor swept area is proportional to the square of the length of the blades. So you really have, as you get to these larger turbines, this tremendous growth in the power that can be produced. So that's one of the economies of scale that happens. So one of the projects that my team has been involved in is this project that where we're exploring lightweight downwind rotors. And we called our concept the segmented ultralight morphing rotor, or SUMR for short. So I'll explain the terminology a little more in the next slide. So we're bio-inspired by palm trees, which are down here in the lower left. So palm trees on average are about 20 meters tall, so much smaller than everything else here. And in this project, we designed a number of 13 megawatt, 25 megawatt, and 50 megawatt turbines. So at the start of our project in 2016, the average land-based turbine was about 2.5 megawatts. Nowadays, the average land-based turbine is about 3.5 megawatts. All of our 13 megawatt designs had blades longer than 100 meters, and all of our 50 megawatt designs had blades longer than 200 meters. So the rotor diameter is more than 400 meters. So these are really, really large machines. So why downwind? Well, when you have upwind turbines, right, the rotor is in front of the tower, right, and so wind is coming through the rotor before going around the tower. The combination of centrifugal gravitational thrust forces on average pushing the blades backwards. And as these blades get longer, they naturally get a little more flexible, and they're being pushed back more towards the tower. And there's concern of tower strike as that rotor is spinning. And to prevent tower strike, they try to make the blades stiff enough to prevent that tower strike. To make these blades stiff enough means a lot of mass. So these are really massive blades, very, very heavy, and ends up, large capital costs. And so we believe that there will be some size point at which point you really need to turn downwind. So once you turn downwind, you can go with much lighter blades. So they're going to be lighter, more flexible, but much lower capital costs with less material needs to go in the blades, and they're easier to transport, hoist for assembly. Then you have a lighter rotor. That also means that the tower could be lighter. So there are lots of downstream kind of lower costs that could happen. And so the idea is then you have these downwind, lightweight blades. They will naturally morph with the wind. And so then when you have very light winds, the blades will be pretty much wide open, trying to maximize power production. As wind speeds increase, they'll morph with the wind and essentially try to load a line with the wind. Instead of fighting with the wind, they'll line with the wind. That will reduce the structural loads inside the blades and also will naturally kind of regulate the power at those higher wind speeds. So we're bio-inspired by palm trees, which do just that. They kind of morph with the wind, they're lightweight, they can survive these hurricane conditions, which is something of concern in the US East Coast in particular. And so this is in contrast here. So this is an actual photo from a hurricane. In the foreground here, there is a massive oak tree, which has actually been toppled over by the hurricane forces. And so that massive oak tree essentially is trying to be as rigid and massive and fighting against the wind, but in the end, it got toppled over, whereas the palm trees going with the flow were able to survive the hurricane conditions. So that's kind of the inspiration for our simmer design. Now, one other aspect, the segmented part, is an aspect that our structural colleagues were investigating. So blades, for the most part, are manufactured in one piece these days. So as you get to these 100+ meter blades, it's very complicated to transport them. And so there are a number of teams investigating whether it might make sense to manufacture blades in segments. That certainly would simplify the transportation issues. But the big question is, when you get to the site and put them all back together, will that blade, have the structural integrity to last the 20 or plus years that we want these blades to last? And so that's still the big question. Okay, so I'm not going to talk more about the segmentation part. That's not something that we in my group have directly worked on, but it is an active area of research. Okay, so now in designing these downwind turbines, we went through the entire wind turbine design process, which traditionally is pretty sequential, where the aerodynamical design is done first, followed by the structural design, followed by the control design. So my research group has expertise in the control systems aspects, so we are focused on the control design. Usually by the time we're asked to design controllers for a wind turbine, the entire wind turbine has already been designed. And we're just asked to design the best controllers to try to maximize power production or regulate power production and reduce structural loads. So just to give a little more detail, the aerodynamical design is concerned with the geometry of the wind turbine. So what is the shape of the blades? The structural experts then determine the material layup needed down to the detail of the orientation of the fibers. And they want to ensure that the blades, for instance, will last the 20+ years of the lifetime of the wind turbine. Now, we'd like to think of the control system as the brains of the wind turbine system, right? So the control system is making use of the measurements from sensors, monitoring the wind turbine, and based on those sensor measurements, deciding, do we need to pitch the blades more? Do we need to yaw the turbine in order to maximize power production or reduce structural loads? Now, when you have a sequential design process, there's some conservatism at each step. So for instance, the structural designers, they might end up putting more material into the blades to make sure that that blade will last the 20+ years. They're not quite sure how well the control system is going to work. So they, just to be safe, they put more material into the blades. And so what we ended up doing in this project, we initially used that sequential design process, but then we had some really aggressive milestones that we needed to meet, and we ended up backing into what we call a control co-design process, because we found that that sequential process was not going to allow us to meet our milestones. So we ended up working more like this, where we would pass back intermediate control algorithms to the other teams for them to use. And so, for instance, the structural team found that our controllers would mitigate the vibrations really well. So they didn't need all that material in the blades. They could actually remove more material from various portions of the blades to reduce the capital cost. And so ultimately, through this control co-design process, we were aiming to try to minimize that levelized cost of wind energy. And through this co-design process, we were actually able to achieve 25% reduction in the cost of wind energy in a lightweight two-bladed downwind rotor wind turbine relative to a traditional three-bladed upwind turbine at that same 13 megawatt scale. And so this was pretty exciting, and we're actually still continuing to use control co-design in a number of ongoing projects. So in order to fully demonstrate the lightweight downwind rotor concept, we also did field testing. So one of the 13 megawatt designs that we had, we gravel aero elastically scaled down by to 20% scale. So the original 13 megawatt turbine had 105 meter blades, and then we scaled down. And so we had 21 meter blades that were actually then manufactured and first ground tested, and then ultimately hoisted onto a research turbine at NREL. And we ran through an entire kind of measurement campaign that lasted about 10 months from 2019 to through the summer of 2020. So I have two videos here. So this first video is actually nominally of the wind turbine in a parked position, but when there are winds, you'll still see it rotate. And the point of this video is to show just how flexible the blades are. So as the rotor's spinning a little bit here, if you look closely, you hopefully see the blades flexing. So these are really pretty flexible blades. Then the next video shows the wind turbine in operation. And so it's downwind, see relative to the nearby other three-bladed upwind turbines. And you can see that downwind coning, and we actually, through all the field testing, we were able to demonstrate that downwind load alignment and low structural loads. And so the field testing was quite successful. We tested out that load alignment, low structural load concept. This wind site, it's placed where it is because it has really pretty turbulent high wind conditions. So we survived. These blades were on the turbine across several winters, and those were the highest wind seasons in Colorado, and survived over 50 meter per second winds in high turbulence. That's more than 110 miles per hour. And so a number of our papers analyzing kind of those initial results have been published, and we're continuing to analyze some aspects further. So one of the things we learned from the project where we were looking at levelized costs of energy as the metric was to really understand, try to think about how can controls contribute to that. And so what we realize is that one of the best ways controls can help is that we want to try to boost power production whenever possible, while ensuring that the structural loads don't exceed kind of the desired thresholds. And so we've now developed an advanced controller that does just that, using the measurements available. If the wind turbine is operating very safely, far away from any of these thresholds, and wind speeds seem to be relatively steady, then we can actually boost power production by 5 or 10% to try to maximize power production. But if we're monitoring and we see that the wind turbine has a lot more variability in its states, and it's getting closer at times to these safety boundaries, and we also notice that the wind speeds are also changing quite a bit, then we'll actually derate even lower than the traditional industry standard controller, just to be safer, because we don't want to exceed these safety thresholds. Usually when these safety thresholds are exceeded, then the turbine will automatically be shut down, and then you'll really lose a lot of energy production. And so in reasonably high fidelity simulation, this advanced controller has been shown to yield approximately 5% increases in annual energy production, while the structural loads are relatively unchanged. And so that's been pretty exciting. Now, we were trying to race in developing this controller, but we were not able to test it on the field turbine. It's really expensive to maintain the fuel turbine, so ultimately it had to be taken down, and we didn't have time to actually test this against a controller on that turbine. However, as part of my sabbatical last semester, I was in Germany spending time at the Wind Center for Wind Energy Research at Oldenburg University, and in discussions with them, they're interested in us testing this advanced controller in their wind tunnel facility. They've been gearing up for this test. My PhD student, Mandar Fandis, joined me out there in November. We've been gearing up for the test. I handed off everything that I got to him, and he's actually still there. He'll be there till early April, and our wind tunnel window is coming up in a couple weeks. So actually be testing. So this is the Wind building. The wind tunnel is on this right-hand side, and now testing in the wind tunnel facility. Yeah, Jack, do you have a question?
Oh, sure. Robin, can you ask questions? I'm not sure what's the etiquette.
If it's for clarification.
Yeah,
I'm fine.
No, it's what you're having for dinner, maybe not.
May I ask to what extent the control design is limited by kind of longevity concerns? Sometimes in these applications, we'd like to use a more active controller, but we just wear out the actuator too much. Is that a concern?
That is a concern, yes. And when we talk with industry, they are definitely very concerned, and so they often they ask the question, we're doing so much better in the controls. They ask us, well, how much are we pitching? And so they want to know how much actuator usage we are using. And so there is that trade-off. And so we are often penalizing actuator usage so that we only use it when it's really providing a big benefit. Yeah, that's a great question. Yeah. All right. So testing in the wind tunnel is not inexpensive, but certainly less expensive than doing the open field testing we were doing at NREL. The other big advantage there, not sure what's happening here, okay, is that at this facility, they have this controllable grid that they can place in front of the inlet to where the wind comes into the tunnel, and they can essentially control the turbulence that's coming in, and they can reproduce relatively accurately turbulence that's in the field. Okay, so we're doing our testing then on these 1.8 meter rotor diameter model turbines. They're called Molito for model wind turbine Oldenburg, and these model turbines have all the sensing and actuation capabilities that we need for testing of the advanced controllers. And so the nice thing then in testing the wind tunnel is we can repeat realistic turbulence conditions and evaluate, industry standard controller versus advanced controller, and really evaluate kind of the advantages or disadvantages of different approaches. And so I got this video from the Wind website, and this will show that controllable grid where there are these vanes, and you can control them to get the realistic turbulent inflow conditions that you want. So we're really excited to be able to test this out. All right. So now I'd like to turn to talking about floating wind turbines. And maybe before doing that, in case if there are any other questions.
On the traditional upwind design, you can you vary the angle a bit? Is that what you're saying by pitch? You can vary the angle of the tank?
Yes.
Is that not enough then to kind of shed those kind of dangerous loads with?
Yeah, so for the upwind turbines, yes, there is pitch control, the blade pitch control. So typically when you get to above rated wind conditions, there's two types of blade pitch control. There's collective blade pitch control. So as the average wind speed gets higher and higher, the blade pitch of all the blades will pitch more and more to let more wind go by so that you regulate the power at the rated power. Then you can also do individual pitch, so where every blade pitches a little bit differently based on the conditions it's seeing.
Do the two-bladed turbine has to go around faster than the three-blade? What's the trade-off?
So the two-bladed designs relative to three-bladed designs, the blades are actually larger. Yeah. We try to keep that tip speed down because of noise concerns. Yes.
One last thing, I was like, I'm sure it is better to kind of reduce mass if you can do, it makes it cheaper and things, but I wonder if like looking at kind of the system more broadly, maybe it's in some senses useful to have the mass as it's like rotating mass and it gives you inertia, so if you're thinking about kind of electrical
Power quality.
yeah, exactly. Yeah.
I think it's still very massive. We're trying to drive down the capital costs and balance of station costs. And so I think from the point of view of power quality, I don't think having more mass is necessarily better. Any other questions? Okay. All right, so now turning to offshore wind. Talk about floating offshore wind, but maybe first just in general, so why are we interested in offshore wind? So in the US so far, we have very little offshore wind, but there's still a reason to have interest in offshore wind, and some of these reasons are really like, similar across many countries. So generally, to go offshore, you have stronger, more consistent winds. Oftentimes you have large cities on the coast, so it makes sense to be generating electrical power near where it's needed. And as mentioned earlier, once we go offshore, there are few constraints on turbine size. So it can really go to these much larger turbine sizes to try to drive down the cost of energy. All right, now let's look at the growth of offshore wind power. So earlier we were looking at the growth of all power, land and offshore. And so to recap, at the end of 2022, there's 906 gigawatts of wind power globally. Average annual growth rate over the last decade was 12%. So looking at offshore wind only, the average annual growth rate is almost 3 times faster at about 33% per year. So at the end of 2022, there was 59 gigawatts of offshore wind. If you take that 59 divided by 906, that's was 7% of all wind. And so it's still a pretty small percent of all wind, but it is expected that offshore wind will continue to grow much faster than land-based wind. And so it's expected that offshore wind will become a significant fraction of overall wind. Now, in terms of country, which country has the most offshore wind? UK was number one. It's China. Yeah. So China has had this tremendous growth rate. And if you move this over, you can see that.
You're hiding it.
So what country is number 2? It is the UK. So UK was number 1 until this year. There, you can see that huge growth in Chinese offshore installations. What country is number 3? Actually, Germany. Yeah. And so now, how much of each country's wind, installed wind power is offshore? It's going to vary a lot depending on the amount of coastline, amount of offshore wind resource. So the UK, half of overall wind power is offshore. Relatively small country, great offshore wind resource. All right. Now, right now, offshore wind is dominated by these 7 countries. And there's not much offshore wind elsewhere in the world. But that's changing. There's a lot of upcoming offshore wind projects that are being built in a number of other regions around the world. And so I think over the next few years, we'll see more countries on this pie chart. Okay. Mhm.
I was just wondering, what does the percentages mean exactly? Because I'm from Belgium and I can feel like Belgium 4%. But what,
So this is like China has 46% of the offshore wind power installed
in like worldwide?
worldwide. Yeah, yeah. Belgium has 4%. Yeah, which is also very impressive, right? It's a small country.
I
Yeah,
think that I-
yeah,
I-
exactly. Yeah.
I-
Okay. All right. So more than 99% of offshore wind turbines right now are what are called fixed bottom offshore wind turbines. These are where the turbines are built all the way down into the sea floor. Now, when you get into deeper waters, in roughly 60 meters deep is considered kind of that dividing line. Once you get deeper than that, it doesn't really make economical sense to build those wind turbines all the way down into the ocean floor. And so floating platforms have been considered, and looking at floating wind turbines. So once you have floating wind turbines, both the wind and waves will affect the wind turbine motion. You'll have oscillations, and the control problem actually becomes more challenging. So this shows the offshore wind around the world, and globally, the majority of offshore wind resources are over water depths greater than 60 meters deep. So eventually, floating offshore wind is expected to be a significant fraction of overall wind. And so if we look at where floating offshore wind is being considered, so in the US, almost the entire West Coast is deep water, the Northeast Atlantic as well. And floating wind is being considered around Hawaii and also over the Great Lakes in around Michigan, in that area. And that's mostly actually deep water there. In South America, floating wind is expected to be initially be developed off the coast of Brazil. Many locations in Europe are considering floating wind, and a number of locations in East Asia as well. So right now, there are about 200 megawatts of installed floating wind power, primarily all in Europe. So there's Highwind, Scotland, there's Windfloat Atlantic off the coast of Portugal. There's Kincardine off of Scotland, and there's Highwind Hampton off the coast of Norway. And so all of those are relatively small floating wind farms. They amount in total to 193 megawatts. So looking back at this wind resource map around the UK, it's very strong winds in the UK and off the coast. So if we add off this water depth map here, you'll see that the North Sea has a lot of shallow water, which is why there's so many wind farms that fit there. But yeah, around the UK, there are deep water sites, and I think those are coming. Again, the UK's goal is to develop up to 50 gigawatts of offshore wind by 2030, is it? That they are expecting about 5 gigawatts of that to be floating offshore.
Typically, how far away would the fixed bottom and the floating turbines be from the shore? Like, would they be very visible, or?
So typically the floating will be further away. I think the 4 small floating wind farms, 3 of them are about 20 to 30 kilometers offshore. The latest one that went into operation, Highland Hampton, is something like 140 kilometers offshore. Pretty far. Yeah, and it's in 200 to 300 meter deep water. So it's really deep. Yeah. Okay, that answer your question?
Yeah, I was just saying, because I think I read something about how they were potentially putting these offshore turbines in Cape Cod, But then people were saying that it would impact tourism because it doesn't look nice.
Yeah.
But I don't.
Yeah, I think those are actually, I think for the most part, the shallow water
Okay.
sites. Yeah. Question?
When you said on the previous slide that the majority of wind resource would be floating, is that sort of close to 50% or 90%?
It varies. So in the US, it's something like 60% of the offshore wind resource is over deep water. In Europe, it's actually 80% of the offshore wind resource is over deep water. So it varies from region to region.
Is that within 200 kilometers?
It's within whatever is considered waters that each country can
Is that
build.
200 nautical miles?
Something, yeah.
Total resources is huge, way more than we use.
Right.
More energy, so.
Right. Okay. All right, so some of the initial floating platforms that have been considered have been essentially borrowed from the oil and gas industry. So these end up being really massive structures. That means a lot of capital costs, a lot of material needs to go into these structures. But the flip side is they are actually relatively sturdy. So you don't get too much motion rocking them. Okay, so there's a lot of drive to reduce that capital cost, to reduce the cost of those floating platforms. So get to talking more about that. So let's look at the two main types of floating platforms that have been used. So of the 4 small floating offshore wind farms that exist right now, 2 use what are known as spar platforms, and 2 of those small floating wind farms use what are known as semi-submersible platforms. And so these are actual photographs of these platforms. You can't quite see into the water there, so I'm going to use a diagram or this illustration to explain how these work. Okay, so the spar platform achieves stability by having a really deep draft. Okay, but the downside of that is that most ports are not deep enough. And so you can't assemble these turbines at port. So you have to transport the components out to essentially where those wind turbines will go, and then do the assembly out in that open water. So that adds some complexity. Now, the semi-submersible, on the other hand, it achieves stability by distributing buoyancy across a much wider plane. It has a shallower draft, and that then enables these semi-submersible floating turbines to often be assembled at port. And then they can actually be towed out to where they need to be by a regular tugboat. So that's what was done in the Windfloat Atlantic project. And so that's a really huge advantage for semi-submersibles. And if you look at the pipeline of floating offshore wind farms that have been announced and where they specify the likely floating platform technology they'll use, semi-submersible is the most popular. The downside of the semi-submersible platform is because it has kind of this wider plane, it has kind of more of that platform above the water line, and it's then more exposed to wave impacts. And so that then has to be handled carefully. So one of the projects that we've gotten involved in over the last few years is this US Float project. US Float stands for Ultra Flexible Smart Floating Offshore Wind Turbine. And essentially, it consists of a DTU, Danish Technical University, 10 megawatt reference wind turbine on top of a novel lightweight substructure, which we call the spider float. So when we refer to spider float, we're referring to the lightweight platform. And when we refer to US float, we're referring to the entire floating wind turbine. And so here we were doing control co-design just between the structural design of the floating platform and the wind turbine controls. Basically, our teammates, the structural experts, they were trying to essentially decrease the cost of the spider float platform, and that largely meant decreasing the mass of the spider float platform. And then our job on the control side was to make sure the controllers still stabilized that floating wind turbine. And so there was a lot of back and forth in terms of how much mass they could remove.
So
Question?
it's definitely like more complex to install like offshore wind turbine than average like wind turbine. But I was wondering, why should we promote offshore wind turbine instead of like wind farm or normal wind turbine? Like,
You're saying compared to land-based?
yeah, exactly. I was wondering, like, does the offshore wind turbine provide more efficient energy, or is there, like,
And that's a
an
great
advantage?
question. So in terms of cost of energy, land-based wind energy is the lowest cost on average. And so, but you tend to get more pushback from people for land-based wind farms. And I think that's what's happened here in the UK. And there's been tremendous growth in the offshore wind, but very much slower growth in land-based wind. And so that's that trade-off. So offshore wind in particular, if it's far enough where people can't see, people tend not to object.
I'm assuming there's a capacity factor argument. There's more availability of the wind on offshore locations. The wind droughts are maybe less frequent.
Right. Yeah, so yeah, there's more consistent, stronger winds offshore.
Use to the difference in LCOE between shallow and deep water.
Yes, so floating wind has much more expensive LCOE at the moment. It's expected that with development, that levelized cost of energy for floating wind will come down to the same level as for fixed bottom wind. And so then it will become a matter of just what does the site need? Does it need fixed bottom or floating? You choose the technology that's most appropriate. Yeah.
That's a really dumb question.
Yeah, no.
Land-based wind turbines, like the energy gets transmitted through the pylon and stuff, like on land, right?
Mhm.
How does that work with?
Yeah, so for offshore wind, yeah, that power has to be transmitted back to, so the power cables. Yeah.
Underwater.
So usually they lie on the sea floor, ocean floor, right? Yeah. And that gets into sort of partly also why there's that economy of scale going to larger turbines, right? If you have, say, 100 megawatt wind farm, you could have 42.5 megawatt turbines or 250 megawatt turbines, right? So it's easier to maintain, and the power cabling that's needed is less for larger turbines.
And I'm just going to say my understanding is there are some proposals to have offshore connection points. So you put in the grid and then allow farms to connect to it.
Right.
The difficulty is building that ahead of the wind.
Exactly. And that's a whole big discussion. Exactly. Right. Right. Yeah. All right. Yeah, so this is a video showing kind of our US float configuration in action. So the US float, you can see that it's kind of maybe semi-submersible inspired, but trying to remove mass where possible. So it's designed to be modular so that it's for ease of manufacturing. So essentially there are multiple legs. There are these cables that attach to the legs. And there are these buoyancy can clusters that are attached through universal joints to the legs as well. And these buoyancy cans, one of their big advantages and part of the design is to try to dissipate the waves before they impact that tower. So try to mitigate the wave impacts onto the tower itself and onto that turbine itself. And so this US float project is now continued into a phase 2, where we're actually going to be doing some water testing and to really try to see how far we can push this technology. All right, another new project that just launched is also a phase 2. We were also involved in phase 1 of this, but now becoming more involved in phase 2. So this is the wind energy with integrated servo control and WISE phase 2. The goal of this project is to develop an open source tool set to enable controls co-design for floating wind turbines. And we had backed into co-design in that SUMR project. We were trying to meet our milestones. We kind of backed into doing co-design. We came up with a scheme that seemed to work well. Now we're trying to take a step back and trying to understand that co-design process better. What are the design coupling variables that we really need to include in that optimization process? And something else that we are also trying to do is to try to automate, to the extent possible, the controller tuning process. The other thing we found out through that SUMR process, right, we had many downwind turbine designs. We went through probably 80 downwind turbine designs in all of that optimization. And we found out that the aero team could update the aero design much faster than we could tune even the most baseline controller. And same with the structures team. They could update their structural design faster than we could tune the control. So the other team members, they kept throwing wind turbine designs at us, as we like to refer to. And we couldn't keep up tuning even the most basic controller design. So my student and I at the time were like, okay, we need to come up with a different approach here. So we started looking at automating the controller design. And there's still a lot of work to be done, but we released a reference open source controller that does some automation of baseline controllers. And that's actually had quite a bit of uptake around the world, which has been fantastic to see. And so non-controls experts are using it so that they don't need a controls team to tune their controllers, and they can evaluate different wind turbine designs from aero structural points of view. And ROS is also being used by controls teams to get to a baseline controller that serves then as the reference point. And we can spend more time developing advanced controllers to really bring out what a novel wind turbine concept is aiming to do. And so we're now continuing to develop, we're trying to, and as we develop advanced controllers, we're always thinking, can we automate this? And so we're trying to automate some of the advanced pieces that we can develop as well. Right, so in summary, this aerostructural control co-design really been a lot of fun. We've learned a lot by working closely with aerodynamicists and structural dynamicists, and this true overall co-design really does lead to more optimized wind turbine designs that can lead to lower costs of wind energy. So far with the floating wind turbine co-design, we've just done structural control co-design. We'd like to throw back in the aero part there, because in our project earlier, we were just using that reference turbine on top of this novel platform. But, and that's what's been done for the most part for floating wind turbines. You take a standard fixed bottom turbine, put it on top of a floating platform. But if you know that wind turbine's going to go on a floating platform, are there things about that wind turbine that you might design a little bit differently? So we'd like to do some investigation there through true co-design for floating wind turbines. So we believe floating wind is really just about to take off in terms of larger installation. Really expected to grow rapidly over the next several decades. And the cost of floating wind is expected to come down to about parity with fixed bottom wind energy. A number of groups are exploring trying to reduce that cost of that floating platform. And it does make the control more challenging. If you want to hear more about the controls of floating platforms, I am giving a control group seminar tomorrow at 2 p.m. in IED LR8, and I'll get into a little more depth about some of the control algorithms we use to really try to stabilize these complex structures. So in terms of ongoing and future work, I'd like to highlight just a little bit of thoughts on control at the wind farm level. So control of wind farms is actually a really active research area for land-based and fixed bottom wind farms. Usually on wind farms, what's done is each turbine is controlled to be as greedy as possible, each turbine tries to produce as much power as it can. And the hope is that across the wind farm, that maximizes power production. But it's relatively agreed upon that that end result does not happen because there are these wake interactions. So this is a relatively famous picture now of a shallow water offshore wind farm off the coast of Denmark. When that lead row extracts power from the wind, you can see wakes are generated behind. There are lower wind speeds in the wakes, more turbulent winds in the wakes. So these rear turbines can't produce as much power because of the lower wind speeds. They also get beat up more structurally because of the higher turbulence. And there's been work done that shows that by coordinating the control of the individual wind turbines, taking into account these wake interactions, you can actually lead to much higher power production across the wind farm compared to each turbine being as greedy approach. Now, for floating wind, there's some interesting questions. One is, how do the wakes propagate behind a floating turbine? The intuition is that since the floating turbine's moving, the wake behind it is going to dissipate faster. Now, there's some scientific results that are just coming up now from a number of more atmospheric and oceanic sciences researchers that are showing that that indeed is the case. And that's exciting because if wakes behind floating turbines dissipate faster, you have less wake effects. And so that means for the same layout, a floating wind farm will be able to produce more power than a fixed bottom wind farm, or you can pack more turbines into a floating wind farm. Now, the other interesting aspect for floating wind farms is that for these floating turbines, while there are usually mooring lines, they are relatively slack. And so these floating wind turbines could be controlled to move a little bit laterally. So then you could re-optimize the layout slightly depending on the current prevailing wind conditions. So then you can kind of sort of maximize that power production from floating wind farms in a way that you wouldn't be able to do with fixed bottom wind farms. So there are a lot of promising directions to explore for floating wind farms. So I'd like to thank our funding sponsors who have supported our work in the wind energy area over the last 5 years or so. In particular, ARPA-E, that's the Advanced Research Projects Agency Energy in the U.S. They supported the SUMER project, the U.S. Flow project, and now the WISE Phase 2 project. So I want to thank the SUMER project team. This is the team photo when one of our blades, the 21-meter blades, came in ready for ground testing. And so you can see it's a relatively large team. We've learned so much from interacting with the aerodynamicists and structural dynamicists. Also want to thank the U.S. float team. These are most of the institutional leads on our project. Mario Garcia-Sanz is actually the program director of the funded us. And then I also want to thank my research group. This has actually become the standard way that we take our group photos. So Mandar is the student who's in Oldenburg in Germany, about to go into the wind tunnel for testing the advanced controller. Nikhar Abbas is the main student behind the Roscoe controller that was open source and is used quite widely now. So he, for that reason, was chosen to receive the 2023 European Academy of Wind Energy's Excellent Wind Doctor Award. He's now working full-time at Siemens Gamesa Renewable Energy in Copenhagen. And Manuel Puch was a postdoc, worked at both US Float and SUMER, is now a professor at Hochschule München, so Munich University of Applied Sciences. So David Stockhouse is the main student working on the control of floating wind turbines. Eva Henry is now working on control of wind farms. And I want to thank all of you for being here. Thanks for your attention and interest.
Application of having little sail attached to the floating turbine that will tack up and down wind.
Yeah, there you go.
I had a quick question, which was around risk, because you can see conservative design engineering. We know how to build a platform at sea. We know how to build a wind turbine. You must have an influence about the cost of capital because you understand the risk associated with that. So even if you have a cheaper, lighter design, the risk associated with a lack of understanding of that must affect the cost of capital. So
Yes.
can you just interplay the capital cost versus the materials cost, if you like?
Right. So that definitely there's a trade-off. But I think with these initial platform designs, they were initially inspired, transferred from the oil and gas industry and adapted for floating wind turbines. And I think by designing floating platforms more targeted for the floating wind energy application, that probably a lot of performance can be gained by doing that. And I think in the wind industry, that they are conservative. We talked about this earlier. So I think we're going to go with probably even novel designs, probably a little more massive at first, just to make sure, and then get some of those out in the water tested before really trying to reduce mass.
Thank you. So thanks very much for taking questions on the go. I don't know if that means we've exhausted all the questions in the room already. Nick has a question.
Going offshore for wind, I've heard it mentioned, but not in any detail, that this might open up the options for wave energy again by integrating wave with wind. I mean, it's been a 40-year disaster story. I know wave energy, I know that, but it is. What do you think?
I think I'm excited about the having wave energy converters near floating wind farms, right? So I think the wave energy converters could dissipate some of the energy from the waves before those waves might impact floating wind turbines. So I think that could be a win-win situation.
Presumably, it's not interesting.
Right, right. But then, you know, you're making use of the same power cables, right?
But there are already moving parts on some of these floating platforms anyway, and a moving part in an ocean environment sounds quite tricky. So if we can solve that, then maybe waves are just too strong, aren't they? You need to go somewhere much calmer. Sorry, you had a question.
Yeah. So we've seen a couple of bottlenecks on the shipping side, sort of follow these structure. Do you think that sort of moving to a floating design solves that to some extent, or debottlenecks that, or is that still in the future?
I think it may provide additional options. I think obviously having all the players that use that offshore region talking to each other is necessary, so that everybody kind of has their voices heard and we can come up, you know, it's like co-design, right? Having everybody discuss and really coming up with a co-optimal solution.
Because you talked about segmented rates, for example, but is there also opportunity to relook about the materials used, because you're now controlling the surfaces more in response to the situation? So instead of a conservative, again, traditional design technique, could you choose a different class of materials for your blades?
Possibly, yeah. I think a little bit when you talk with local communities, and sometimes they want you to use local resources, right? So that gets into maybe you don't use materials that need to be imported, and so you get into I think all of those questions come up, and I think again, I think it's we've been actually trying to get into some larger projects, really co-design with the social side, which gets really complicated, but all of that needs just more discussions with the people, the communities, and coming up with a solution that everyone can get behind.
I feel the learning effect will be as strong. You take the example of 25 4-megawatt turbines and 2 50 watts. So learning comes about when you're making quite a few things. I'm thinking of a nuclear power where people have gone really enormous ones and we've stopped the learning effect. Do you think there's any danger in that in the wind? That you're making 2 larger ones, you're not going to be making that
as much learning. Yeah, I mean, so I think at the scales that we're talking about needing to deploy more and more wind, I think there are going to be plenty of these large turbines still. So I think there'll still be plenty of learning. There have been discussions of, at what size will we not grow anymore beyond that? And so that is maybe a question that'll come up as we push beyond 17 megawatts, 20 megawatts. So.
the mechanical stress limit on some part of it?
Yeah, we don't know. So the 50 megawatt, we've done relatively, I'd say medium fidelity simulations. Of course, there's a question of how well that simulation captures everything. And there's still some open questions in terms of unsteady aerodynamics and such that still need to be built into the simulation tools. But to the extent that we evaluated, it seems like it could work.
Bending our understanding of materials and make sure that
Exactly.
it keeps delivering a bit further. We're trying to stretch materials for a number of applications, like
absolutely.
fusion power. We don't even invent some of those yet. So we're
Yeah.
still planning ahead, hoping material science comes up with solutions. So,
And so in terms of going to downwind, we definitely still think there is a size point where we'll have to turn downwind. But the industry really wants to stick with the upwind, the three-bladed upwind, because all their manufacturing processes, everything's set for the three-bladed upwind. And they're banking on novel materials to be able to continue to keep those blades stiff enough without getting too massive.
thanks very much for not using lots of control equations and so on. I did do that. Yeah, tomorrow, if you sleep in the lack of it. So shall we say thanks once more to Lucy? Very quick output for next week. We're looking forward to hearing from Jose Maria Valenzuela on centralization, state intervention, and the redistribution of power in energy markets. And that will be back here. Thanks again for coming this evening.